Hi, my name is Max Colombara.
And my name is Timothy Wagner.
We're part of the IB Simplified 101 channel. Today we're going to be covering Unit 3 of the Math Analysis and Approaches Standard Level course. The following units are covered in the first semester of this 2-year long course. In this video, we're going to be covering Unit 3, Exponents and Logarithms. Quick disclaimer, as always, all of these videos function as introductory content or as review. So do not use this to actually process or properly learn these concepts. This is especially true for today because 80% of this unit is actually review from past years, depending on what classes you might have taken, but it is still around 60 to 80% review. And then the other 20 to 40%, which is logarithms, which may or may not be new, but under this context, we're going to say it is new. The variety of potential problems is so huge that we're just going to establish the tools that you need to solve these exponential problems. Quick introduction, a quick review, but we're not going to dive into the actual problems due to the sheer diversity of these.
Okay, rules of exponents. This is probably a review for you, but as you know, the product rule, when you multiply two same variables and they have exponents, you add them together. Then the quotient rule, it's basically the same, but the opposite. You have two of the same variables with different exponents, you can subtract it. Then the power rule, there's a parentheses variable with an exponent above it. And then on top of that, this parentheses has an exponent. You multiply both exponents together. And then the power of a product rule means that if there's two variables in a parentheses and they're both, and that parentheses is raised to a power, then both of them will receive that power. Then the power of a fraction is the same. If there's a fraction, both the numerator and the denominator will get the exponent. Zero exponent, any variable, any number to the power of 0 will always be 1, except 0. Negative exponents, it's, well, instead of increasing the size, it diminishes the size into a fraction. You put the variable below and put as a numerator 1. Then a fractional exponent is x divided by y. It eventually turns into a of x, square root of a of x to the root of y.
As Samuel was saying, this portion of the unit is just review, but it is important. So there are two parts of scientific notation. And the first of it is understanding how positive and negative powers influence a number. And this might sound very basic, but it's just a reminder and an important component. So negative powers essentially, because we should already know how positive powers function, but just a review of how negative powers function. If we have a negative power, basically we're going to be taking the exponent of the absolute value of that negative number. So 10 to the power of negative 2 is really just going to be 10 to the power of 2, right, which is 100. But then that number being the denominator, right, and the numerator being 1. So you're just uh, you're dividing 1 by 10 to the power of the absolute value of the negative number, if that makes sense, using the previous knowledge that we had of the absolute value. And the second component of scientific notation is the actual notation. So, based on this, right, based on how we know exponents interact with a base 10 specifically, we're going to be able to do a scientific notation where we have a, our coefficient, which is going to be between 1 and 10. And we're going to have our other coefficient. So we're going to have one coefficient, another coefficient, which is going to be 10, right? And we're going to have our exponent over this coefficient, right? Where n is an integer, right? And this is going to determine the, you could think of it as it's going to determine the decimal value of a, our coefficient, our value. So our a is going to be our coefficient of 10 to the power of n, and 10 to the power of n is going to determine the decimal value of our coefficient of our value a. So for example, in the case of, let's pick 8 as a, well, if we have it to the 10 to the power of 6, this is going to result in 800,000, right? So that's how we can determine the decimal value. And in the other case, we have a negative exponent, we have negative 6, and we're going to have 0. Then a bunch of zeros, and then 8. I don't know if this is thousands, millions, but you get the point, right? The second number and the following exponent is going to determine the decimal value, and a is going to be the coefficient or the actual value of that value, if that makes sense. So it's a way of compressing extremely big numbers or extremely small numbers.
Oh, exponential equations are any base risen to a certain value. The parental function of exponential functions would be 2 to the power of x. It has a correlation with the logarithms, as the manipulation of these allows for the solving of exponential equations without a graphing calculator. And the functions are always positive because you can't, any number times itself, it can never turn out negative because a negative number times itself will give you a positive result, and two positive numbers will still give you a positive result. The horizontal asymptote is 0 since, well, they can never go into negative values, for y at least. And Max,
Oh, I was muted. My bad. My bad. Okay, I'm gonna start now. I am so sorry. I was talking. I am so sorry.
sign.
Okay, I'm
3
gonna start now.
seconds.
Okay. And logarithms. So for the ones of you reviewing, you know what logarithms are. For the ones using this as introductory content, some of you may know what logarithms are, some of you may not know. But essentially, a logarithm is the exponent or power to which a base must be raised to yield a specific given value. So let's provide the following example. Log base 3 argument x equals 9. 9 being the specific given value, right? And if we want to translate this to an exponent or an exponential equation, we're going to have 3 to the power of x equals 9, which Timmy just covered, exponential equations and exponential functions. And this wouldn't necessarily be the parent function, but it would be a transformation of that function. And in this case, x would equal 2. So as we're going to explain in the following slides, logarithms are used to solve exponential equations, such as 3 over x. As you might have seen, 3 over x, you might have tried solving these type of exponential equations before, but you couldn't. You couldn't without a calculator. You would always need a graphing calculator. But logarithms allow us to kind of cheat that and use their rules to solve these equations. And if we go to the right, we can see the formatting of a logarithm, where we have the log, then we have the base, then we have the argument in parentheses, and then we have the exponent or the specific given value. So in the actual definition, right? Definition being logarithm is the exponent or power to which a base must be raised to yield a specific given value, or exponent is our specific given value.
So logarithm rules, these are the rules that allow you to manipulate them. Um, they're pretty simple. The product rule, it's if there's an x and y variable in the same parentheses, then it's adding log a of x plus log a of y. The quotient rule, if you're dividing x over y in the parentheses, then it will be log ax minus log ay. Then the power rule is that if log a and x to the power of p, then it will be log a of x with a coefficient of p. And the change of base rule, you have to do log a of x is equal to log b of x over log b of a. These are rooted in exponent rules since logarithms are derived from exponents. They are very useful for solving exponential equations.
So as Timmy explained, they're very useful for exponential equations. And we're gonna have a variety of logarithmic problems and exponential problems, but they are so wide across the course that you're gonna have to cover that with your teacher. But these are just the tools, the manipulation tools that you're gonna be able to occupy. And within these tools, we must explain logarithmic bases because there are two types of logarithmic bases that you're going to see in this course that are using a certain assumption for the sake of efficiency. So let's start in the left. If we have logs with a logarithm with no base, an argument, and a given value, well, and that given value being 10, well, x is going to be 1. And we may think, why? Well, logs with no base are really just logs with a base of 10. And as I said before, this is an assumption made by mathematicians for the pure sake of efficiency. So when we see a log without a base, the base is just base 10. In the other case where we see ln with, yet again, no base, and the argument x equaling, well, in this case, x, the argument would equal 1. If we ask ourselves why, well, ln is an abbreviation for a natural logarithm. And a natural log has a base of e. So similar to the example to the left, our given value or exponent to the right, our e, is the same as a base. In these cases, x, the argument, is always going to be 1. So if our given value to the right, to the log of the logarithm is the same as a base, then our argument is always going to be 1. So this is why we picked these two examples. So a natural log has a base of e, which is why x equals 1, because this is a log base e, argument x equals e, so x is 1. E is an irrational number, like pi. It is specifically Euler's number, and it approximates to around 2.718, and then it goes on for infinity, which is why it's an irrational number like pi. You don't have to know what Euler's number is, but just use it under the context of natural logs. Well, thank you for watching. This was the IB Simplified 101 channel. This was the whole course review of Math Semester 1, Units 1 through 3. I hope you guys were able to understand these concepts as either introductory or review courses. So I hope you guys were able to flourish throughout this course, understand its concepts. And yet again, as always, this was made by candidates for candidates. Thank you.